You are watching part 27 of a sequence of many videos about parametric curves. It's part 6 of a sub-series about modeling the trajectory of a ball. And in this video we want to get more deeply into some calculus ideas, in particular to ask what it means for the velocity vector to be the derivative of the position vector. So we're going to get more rigorous, still not fully rigorous. If you're in pre-calculus, I still want to make this helpful for you. We are going to come at it from an intuitive geometric standpoint. In order to do so, we need to emphasize the geometric meaning of what it means to multiply a vector by a scalar, a number that scales it up or down in length, and also the geometric meaning of vector addition. Before I do that, though, I think it would be good to type out some text that tries to emphasize what the geometric meaning of the derivative is in the context of a regular function from pre-calculus or calculus 1. Suppose we have a function y equals f of x that is smooth on its entire domain. And we would also, I'm not going to type it out, but we would also assume that that domain is a nice domain. It's either the entire real number line or it's some open interval. And we have a number x equals a in that domain. Okay, so that's the setup here. What is the derivative of this function at a? Well, first of all, smooth intuitively means that the graph has no corners or kinks in it. It's a very smooth graph. It also technically means it has no vertical tangent lines anywhere. The derivative of this function at x equals a will exist in such a situation because the function is changing smoothly, and it's a number that represents the rate of change of that function at that point. The value of the derivative of f at x equals a, denoted by f prime of a, is the rate of change of f near x equals a. Again, that's not very precise. To get a little bit more precise, we'll say this. This means that if you let x change a little bit away from a, if x changes by a small amount, typically called delta x, from x equals a, then the change in y, delta y, is well approximated by the product of f prime of a with delta x. In an approximate equation, we can write that is the change in y is approximately f prime of a times delta x. Okay, let me highlight this, make it red. Okay, again, it's still not a fully precise statement. You know, how good is this approximation? I will say that this approximation gets better and better as delta x gets smaller and smaller, but still that's not fully rigorous yet. But this will give us the intuitive standing to understand more about how the velocity vector is the derivative of the position vector, because what we're going to see is that the change in the position vector can be well approximated by the velocity vector times a change in time. Actually, the independent variable is time in that situation. Let's go back up to our animation. Here is our animation of the motion of a ball as it moves through the air in the upper left, and some other graphs, including the speed graph in the lower right. That's in red. The blue graph is the distance traveled function, and the magenta graph is its tangent line at every point as b changes. b is our animation parameter. I want to focus on just the code that's, or the output that's in the upper left corner of this grid. So what I'm going to do is I'm going to copy and paste the part of this code that gives that graph that was in the upper left corner. Let's copy and paste it down here. I'm going to give this a name. As I have in some previous videos, I've called this paraplot. I'm making my own Mathematica command when I do this. Actually, let's change a few things. Let's make this plot range a bit higher. I'm actually going to change some other things too, but now that I've defined this paraplot of B, I can now put it in Manipulate, and with a very simple looking command, I can generate that graph that was in the upper left corner, and you can now see it's bigger. So there's our ball moving through space. You can see the arrows more clearly now because it's bigger. I'd like to get rid of this aspect ratio. Get rid of that. Now that's going to make the scales more true to life here. It looks like they are the same on both axes. This is more what the actual motion looks like. And now the change in the size of the velocity vector is more accurate. It doesn't change in size a whole lot. It does a little bit. It gets shorter at the top of the motion, and then it gets longer as you go back down toward the x-axis. This is a more accurate representation. Let me make some other changes. I'm going to make the picture bigger. If I put image size arrow large in here, that's an option that's going to make the graph bigger. I think I'm going to also change the coloring. Let's make the parametric plot itself black. Let's make the position vector blue. And the velocity vector, let's make that red. Let's also make the dots smaller now. The ball is going to be smaller now. There we go. What did I say? What's the main point of this video? The main point is that the velocity vector, this red vector, is the derivative of the position vector, the blue vector. It's measuring the rate of change of the blue vector. Did you get that? The velocity vector, the red one, is measuring somehow, in a way we need to make more precise, the rate of change of the blue vector. How is the blue vector changing? It is changing both its length and direction. If you just focus on that blue arrow, it's changing how long it is. It's getting longer and longer and longer. It's also changing the direction. It's rotating clockwise as time goes by. The velocity vector, the red vector, is somehow measuring that rate of change. Running a little low on time. I am going to have to do this in a second video as well. But let's try to add some more to this picture that will start to help us understand what it means for the velocity vector to be the rate of change of the position vector. I want to add another vector to this picture. Let's see. I'm going to copy and paste this. That was the code for the position vector. I'm going to make another vector that's going to be brown. Let's also make it dashed. And what is this vector going to be? This is going to be a position vector as well. It's going to start at the origin, and it's going to go out to C of some input B. What is that input going to be? I'm going to add 0.5 to B in here. What's going to happen? That's essentially going to be a position vector of the motion 0.5 seconds into the future from the blue vector. There we go. That's another position vector, just not at the particular moment in time B that we happen to be at, but 0.5 seconds into the future. What I want you to notice here, what I want you to observe, is that the red vector, the velocity vector, almost points in the direction between the position vector at time B and the position vector at time B plus 0.5. Another thing I'm going to do is I'm going to make this 0.5 even smaller now. Let's go to 0.1. So now we're looking at the blue vector, which is the position vector at time B, and another position vector at time B plus 0.1. And this fact that the velocity vector almost points in the direction between the tip of the position vector at time B and the tip at time B plus 0.5 is even a more accurate approximation in this case. Okay, I want you to dwell on this. I'm going to stop this video right now. I want you to dwell on this, maybe look up some information about vector addition and scalar multiplication, and see if you can't predict what I'm going to talk about in the next video to try to, again, re-emphasize that the velocity vector is the derivative of the position vector.